Okay, welcome back. Today we're going to handle the last section, and this will be the last section for the entire year. I'm so excited. Today we're going to expand on the ideas that we talked about in section 3 and apply them to 3-variable systems. So the catch here is the 3-variable system. The graphical analog is not quite as easy because now you're talking about a 3-dimensional graph. I'm not going to spend any time really trying to talk about how to visualize that or graph things in 3 dimensions, as it's beyond the scope of what we're trying to do in this class. What I'd like to do is just spend a little bit of time talking about how we can apply our methods of substitution and elimination to solve some of these 3-variable systems. So for a 3-variable system, we can use still substitution or elimination. Let's do an example of each. The first example we're going to look at is a substitution example. So let's look at an example. So notice that for a 3-variable system, we have x, y's, and z's in at least one of our equations. Commonly, they would be in all of our equations. Okay. Now, for a substitution, the first thing I want to do is choose a variable to isolate. So again, I'm going to use the same criteria that I used when I was dealing with the 1-variable system. Ideally, I'd want to pick a variable whose leading coefficient is 1. So I see a situation like that in equation C. I'm going to name these A, B, and C. So the first thing I'm going to do is rearrange equation C so that the y is by itself. So if I subtract 6x and 4z from both sides and then divide by -1, this is going to be my new equation for C. What I'm going to do then is I'm going to take that equation for C, or for y, and plug it into the other 2 equations. So my new equation A is going to become 4x, let's color code things, 4x plus 2, and then instead of y, I'm going to write 6x plus 4z plus 1, and then I have plus 3z equals 1. And my new equation for B then is going to be 2x, click that, 2x minus 3, and then instead of y, I'm going to write 6x plus 4z plus 1. And then I just have the rest of equation B. Okay. What I'm going to do now is simplify. So when I distribute the 2 through and I combine my like terms, my new equation A is going to be 16x plus 11z is equal to -1. And my new equation for B is going to be negative 16x minus 7z is equal to -11. And now I'm left with a 2-variable system. So now this becomes the same kind of problem as yesterday. So my first step, my first substitution, takes me from a 3-variable equation with 3 equations and 3 variables down to a 2-variable equations where I have 2 equations, A and B, and they both have x and z in them, just 2 variables. Very important that when you get to this step, you have the same 2 variables in each of your 2 equations. If that's not the case, you've done something wrong, and you should go back and check to find your mistake. But if I look at this equation, this is easy to do with elimination, right? Why would it be so easy to do with elimination? Well, because I already have matching coefficients, or opposite coefficients, I should say, on my x's. I have a 16x and then a negative 16x. So if I just add this down doing elimination, so I just did elimination there, and I didn't have to do anything to eliminate it. I just did equation A plus equation B because the x's already had opposite coefficients. And there I can solve for z by dividing both sides by negative, or by 4. So, next thing I need to do is I need to go back one step and plug this answer into either the equations A or B. So it doesn't matter which one. Let's say I plug this into the equation B. So I have negative 16x minus 7 times negative 3 equals negative 11. So negative 16x minus, plus 21 equals negative 11. So negative 16x equals negative 32. When I divide both sides by negative 16, I get 2. And now I know x and z. So now I'm going to back up to the very beginning. And I'm going to choose one of these three equations and plug in my values for x and z in order to find y. Now the best choice is this one because we don't have any algebra to do because the y is already by itself. So I'm going to take this guy and this guy and plug those both into equation C. So I have y equals 6, but instead of x, we're going to write negative 3 plus 4. X is 2. Goodness gracious. And instead of z, I'm going to write negative 3. And then I still had a plus 1. So when I do that, I get that y is equal to 1. Now, the standard way we write our answers, we're going to write it as an ordered triple, x, y, z. Always in alphabetical order. Okay, so let's just review what we did there because it was a rather long process. So I started with 3 equations that each had 3 variables. I chose one of the equations and isolated a variable from one of those 3 equations. In this case, it was equation C, and I isolated the y. I then took that value for y, and I substituted it back into the other 2 equations. So I plugged my value for y into A, and then my value for y into B. And then I simplified. That gives me a 2-variable system, right? So I have my new equation from A and my new equation from B. Both of them just have 2 variables in it. I then used either substitution or elimination to solve that 2-variable system. It doesn't really matter. In this case, I chose to use elimination because it seemed to be already set up for elimination because the coefficients were opposite. You could have just as easily used substitution. It might have taken an extra couple of steps, and then the algebra would have gotten a little bit messy because you would have had some fractions. But there's nothing wrong with doing that. And that gives me my first solution when I finish solving with the elimination. Once I have that solution, I'm going to substitute it into one of the previous 2 equations to find the other variable. In this case, I plugged the z in to find the x. So that's what I did here to give me x. Now that I have z and x, I can go back to one of the previous 3-variable system or 3-variable equations, plug in my value for x and z to find y. I chose to use this one because the y was already isolated. Okay, so let's do an elimination example. So we'll do another example, but this time we're going to solve this by elimination. So here's my equations A, B, and C. So here, just like we did before, we're looking for an equation or a variable in an equation to use to eliminate that same variable from the other two equations. Basically, I'm looking for a variable whose leading coefficient is 1 or whose leading coefficient is a divisor of that same variable's leading coefficient in the other equations. So here we have lots of choice because the x in equation C has a leading coefficient of 1, the y in equation A has a leading coefficient of 1, and the z in equation B has a leading coefficient of 1. So it doesn't really matter which one we choose to do. Let's say for the sake of arguments, I'm going to choose to use equation B. So I'm going to eliminate the z's from equation A and equation C using equation B. So let's look at equation A first. What do I have to multiply equation B by to eliminate the z's from equation A? Well, I need this to be a 2z, so I'll multiply equation B by 2. Okay. So we're going to do 2 times equation B and add it to equation A. Now let's worry about canceling the z's from equation C using equation B. So here I would need the coefficient on z to be -3. So I'll do -3 times equation B plus equation C. And I'm going to write this out for us here just so that we get a handle on what I'm doing. So I'm going to take equation B and I'm going to multiply every coefficient by 2. So 2b is going to give me 6x minus 4y plus 2z equals -4. And then equation A, nothing is changing. And I'm just going to add down. It's going to give me 15x minus 3y equals 6. I'm going to call this equation D. Similarly now, I'm going to do the same thing. So 3 times equation B. So 3 times 6 is 18x. 3 times -2 is +6. 3 times 1 is -3. And then 3 times -2 is +6. And then I have just my equation C. So x plus 4y plus 3z is equal to 7. It's -17x plus 10y equals 13. And I'm going to call this equation equation E. What I have now is a new system of 2 equations. Oops, I got my y over here. So using equations D and E. Now, I can either do a substitution or an elimination, it doesn't really matter which, to solve this 2-variable system. I'm going to choose to do elimination, and I'm going to choose to eliminate the y's, just because, well, neither one of the coefficients on x's or y's is a multiple of the others. So I'm just going to use the y's because the numbers are a little smaller. So the least common multiple between 3 and 10 is 30. So I'm going to do 10 times equation D plus 3 times equation E, because 10 times negative 3 gives me negative 30, and negative 3 times 10 gives me negative 30. So when I do that, I get 150x minus 30y equals 60. And when I do 3 times equation E, I get negative 51 plus 30y equals 39. When I add this down, I get 99x equals 99, or x equals 1. What I'm going to do now is I'm going to plug this into either equations D or E. It doesn't matter which. So I'm going to say plug it into D. And then I'm going to just solve for y. So subtracting 15 from both sides gives me negative 9. And divide both sides by negative 3, I get 3. So now I have an answer for x and y. What I need now is to get my answer for z. To do that, I'm going to go back to one of the 3 variable equations. It doesn't matter which one I choose. I'm going to choose b, just because the leading coefficient on z is 1, and it makes this algebra just like ever so slightly a little easier. So I'm going to take this one and plug it into b. So that gives me 6. But instead of an x, I'm going to put a 1, because x is 1. Minus 2, and then instead of y, I'm going to put a 3, because y is 3. Plus z is equal to negative 2. So 6 minus 6 plus z is equal to negative 2. If I combine my like terms here, 6 and negative 6 is 0. So I'm just left with z equals negative 2. So that gives me my solution, x, y, z. Again, we usually write it as a ordered triple like that. So the last situation that I want to talk about is an infinitely many situations. So let's look at one of those. Okay, so again, we'll call these equations A, B, and C. So it doesn't really matter, again, which variable I'm going to choose to use my elimination one, because I have x's, y's, and z's that all have leading coefficients of 1. My choice, though, is going to be to use equation B and eliminate the z's, because I don't even have to do any multiplications at all. Because if I look, this coefficient of z is already opposite the other 2 coefficients of z. So I can just do a plus b and then c plus b. So when I do a plus b, I get 2x, 2y, the z's give me 0, is equal to 8. And I do c plus b, I get 4x plus 4y, this is negative z plus z is 0, and then equals 4 plus 12 is 16. So this gives me my new system with equations D and E, 2x plus 2y equals 8, and 4x plus 4y equals 16. So I'm going to solve this system by elimination. Let's eliminate the x's. To eliminate the x's, I need to get these x coefficients to be opposite. So the least common multiple of 2 and 4 is just 4. So I'll just do negative 2 times d plus e. So it's going to be negative 4x minus 4y equals negative 16. And then e is just this. And when I add them together, negative 4x plus 4x is 0. Negative 4y plus 4y is 0. Negative 16 plus 16 is 0. So we have the infinitely many solutions situation. Now, this is true, but we can do a little bit better here. So what I'm going to choose to do is I'm going to rewrite this infinitely many solutions as a way to find those infinitely many solutions. So this is like something called a parameterization, because we're going to write this infinitely many solutions in terms of one of the variables so we can find it. Now remember, infinitely many solutions doesn't mean that any x, y, z is going to satisfy this equation. No, sir. There's just an infinite amount of them. So we would like a way to describe how to find that infinite amount. So to do that, what I'm going to do is I'm going to pick either equation D or equation E. It doesn't matter. For the sake of argument, I'm going to pick D. And I'm going to isolate one of the two variables there. It doesn't matter if I get the x by itself or the y by itself. For the sake of argument, I'm going to get the x by itself. So I'll subtract 2y from both sides and then divide both sides by 2. Everybody okay there? So when I write my solution, the x coordinate is going to be found by doing 4 minus y. Since this is in terms of y, I'm going to put a y there. And the last thing I need to do now is find my z. To do that, I'm just going to go back to my original equations and pick one. It doesn't matter which one for the sake of argument. Let's pick a. Since all the coefficients are just 1, that'll make life pretty easy to deal with. So in place of x, I'm going to put 4 minus y, then I have my y, and then z is equal to 3. So what I want to do now is I just want to solve this in terms of z. So negative y plus y is 0. And then if I subtract 4 from both sides, I get z is equal to negative 1. This was a special situation where the z was a constant. Would not be uncommon for you to get the answer for z in terms of y there. But this is describing our infinitely many solutions. So if I pick a value for y, say 0, when I plug 0 in for y, I'd get the ordered pair 4 minus 0, or just 4, 0, and then negative 1. So that's an answer. And maybe I could pick a different value for y, say 1. So when I do that, 4 minus 1 is 3, 1, and negative 1. And by having infinitely many choices that I can choose for y, I can get infinitely many ordered pairs here. And that will describe for me specifically what those infinitely many solutions are. So I can find as many as I want because I can just keep picking y's over and over again. But that should do it. You should have enough now to be able to do the homework. And that's the last topic we need to talk about for this year. So congratulations. Have a great summer, and we'll hopefully see you in the fall.